Sir, should I start?
Yes, you can start.
Okay, sir, thank you. Good evening, everyone. I hope you all are doing well. This is Safanissa Sreushi, the organizing secretary of the IEEE IUBT student branch. I warmly welcome you all to the final day of our workshop on fuel cells sustainable solution for the future e-mobility. We will begin shortly as a few participants are still joining. Thank you for your patience.
Thank you.
All right, I think we can begin now. Once again, welcome everyone to day 3, the final session of this workshop. It's been a great learning journey over the past 2 days, and we are really glad to have you all today. Before we move forward, let me quickly recap what we have covered so far. In the previous session, we started with the big picture, why the world is shifting from conventional vehicle to electricity mobility, and the need for cleaner and more sustainable energy solutions. Then we move to understanding fuel cells as an alternative to battery-based systems, especially focusing on their advantages like low emission, high efficiency, and faster refueling. We also explored the role of hydrogen as a clean energy source, the basic working principle of fuel cell, including how chemical energy is converted into electrical energy, different type of fuel cell, and finally some practical changes due to and future prospect of this technology. So overall, we have built a strong understanding. Um, Before we continue, let me quickly share a bit feedback from a study session. Overall response were quite positive. Most participants rated the session around 3 to 5 out of 5, which with many finding it clear, useful, and informative. Participants especially appreciated the explanation of mathematical concepts and modeling basics, which helped build a better understanding. At the same time, a few suggestions were noted, such as improving audio clarity, making the session a bit more interactive, and simplifying some part for their easier understanding. So thank you all for your honest feedback. We truly appreciate it and will continue improving the experience. As this is our final day, today's session is going to be especially important as we move further into deeper understanding and practical insights of fuel cell technology. I hope everyone is ready for the last and most engaging part of this workshop. So without taking much time, I would like to invite our trainer to continue today's session. Sir, the stage is on you.
Thank you very much. So today we will mostly do the simulation study in the integrated systems and control. So this is the day 3, and we will be interacting with the practical simulation study of this whole system, whether it is connected to the AC system or it is connected to some resistive load, or it is connected to some reactive loads. So different types of studies we will study in this session. So here we have uh, some system which is showing you the fuel cell integrated with AC load system. Here in this system, we have fuel cell controller. What the fuel cell controller function is, we know that whatever the output here, according to the output and the reference currents, we have some current here which is controlling the fuel cell hydrogen input or fuel input or air input, and it can also control the temperature for maximum power output, as well as for operating the system at particular demanded the operating point. So here you can see this is the accessory to the loads, and here for uh, fuel cell stacks side accessory loads means there are two sections of fuel cell. One section is at constant voltage, which provides the output to the gate drivers and everything. So here main voltage output is through the diode and capacitor. So this diode will charge the capacitor, and the power will never be fed back to the fuel cell, because it will initiate the electrolysis process. So we have to block the DC source, DC voltage here. Now here different types of DC converters can be implemented. It whether it is high gain DC to DC converter, or simple boost converter, or it can be the buck converter. Whatever the converter is here, it is operating as per to achieve the maximum power from fuel cell. Here we have the gate driver, which is controlled according to the maximum power uh, achievement from fuel cell. So to achieve the maximum power, we can either operate the load at maximum power. That is not at all possible, because all times we can change the current and load requirements at different voltage level. So definitely there will be not the same voltage at the output. So for the maximum power extraction from the fuel cell, we have mainly to install a battery in the DC link after the boost converter. This boost converter will provide the boosting of the voltage, and the battery charging current together with the boosted voltage will increase the power level, which ultimately be drawn from the fuel cell. So in this way, we have the maximum power extraction from the fuel cell. So we have understood how the gate drivers control the boost converter. Boost converter here is the same function as was the function in case of the solar. In the solar also, here we voltage and current available from the solar system was boosted, so that the solar system operates at maximum power. And different techniques of maximum power extraction and operating duty cycle was done in the solar system. In the same manner, we can implement the maximum power control of the fuel cell uh, MPPT extraction. Mainly the uh, fuel cell controller, controller will increase the current level. By increasing the current level, we have some control inputs. We can use the single uh, control or multiple control, and here if we use only one control input, then we can control the hydrogen flow rate or hydrogen pressure. Here we can see that if we want to integrate it with the AC load, that is island AC load, not non-connected to the grid, it is isolated load. So simply we have DC to AC converter, that is called the inverter, and for that, for AC harmonics mitigation, we have the output LC filter. Output LC filter is basically a series inductor and a capacitor in every phase, and the capacitors are connected to a common point, that is the three-phase series LC filter. So it mainly minimizes the harmonics present in the uh, harmonics present in the AC obtained from the inverter, because inverter operates mainly at very high frequency, and the high frequency noise uh, can travel to the AC load. Basically, we want the smooth voltage and current, and zero power factor angle for maximum power factor output. So here we have to minimize the harmonics to minimize the THD also. So together with the improvement of power quality, we have to implement this all the system. Here, according to the voltage, phase voltage A and B, we can also control the, we calculate the phase voltage C and current phase current IC. In this way, we have DC to AC control block, and depending on that, we increase the duty cycle of a AC input which we want to achieve here. So depending on the magnitude of the uh, sinusoidal magnitude of duty cycle, we can improve the current and voltage at the AC terminal. So have you all understood this simple system? Am I audible?
Yes, sir.
Okay.
Yes, sir.
Here we have some critical load and non-critical load. What is the critical load and non-critical load? The load which is very necessary to be provided always with the power. So this should have the alternative way of providing the power. Here we have non-critical load directly connected to the utility, and we have some AC to AC voltage controller here. This symbol is for AC voltage controller, a forward and reverse combination of uh, thyristor. So basically, we can control the AC voltage here in the critical load. In case if the utility input is not available, we can not provide the uh, supply to the non-critical load. So that will be not so much problem. If we have some the loss of supply for the critical load, then there may be the problem. So we should have also the alternative path of providing the power to the critical load. So here we have hydrogen cylinder, and there are two parallel combinations. Either combination will work or both the combination will work at 50% capacity. Suppose one of the system fails or some problem there, or it is under repair or maintenance, we can provide the power from this parallel path at 100% capacity. Even the capacity of this system is more than the rated of 100, and we design up to 150%. Any system is designed for taking the power more than its rated. So here we have also the bidirectional power converter, where the power can also be saved to the supercapacitor, as well as during the requirement of instant requirement, transient requirement of the power, we can take the power from the supercapacitor. So here we have the bidirectional converter. Okay, so once we have available DC link here and DC voltage, we can invert it, and depending on the AC voltage available, we can meet the AC voltage requirement of the critical load by using the AC voltage controller. So this is the how the fuel cells are integrated to the critical and non-critical load. Now we see here how the fuel cell is connected to the utility grid. Here we have the same system and DC to AC inverter. Here the series reactor, or we can say that because this is the grid, and line inductance can be modeled here, and available voltage and phase current can be used to control the space vector pulse width modulation using the Parks and Clark's transformation. And the reference signal generator provides the reference current here. So depending on the reference current, the fuel cell flow rate, hydrogen input rate is controlled. So here uh, some we have a transformer which provides the startup power uh, controller. uh, we have some transformer. So electric utility has some is at some upper voltage level, so we need the transformer here. And a 6 load also uh, provided with the power from the separate section of this fuel cell. Okay, so this is easily understandable, everyone. This is the same system as we discussed in the first session. Students.
Yes, sir. It's understandable.
Okay, now we have electric vehicle integration with fuel cell. What are the main parts of this transmission electric vehicle? Hello, hello. 1 minute, sorry. So here we have a vehicle, and these are the wheels representing the wheels of vehicle, and this is the transmission system. Transmission is that means it can be the belt transmission, it can be the gear transmission, it can be eddy current transmission, any types of transmission can be there. And by giving the torque to the motor, the torque of the motor can be transferred to this wheel. So transmission is basically mechanical, and this provides the reduced or increased torque level to this wheel according to the lower torque level of motor, because motors have generally high rpm and low torque. So the transmission can increase the torque of the uh, output side by some gear reduction or some pulley diameter uh, conversion. Here we have DC to AC inverter. We can use the PMSM or we can use the BLDC motor. So for that we have DC to AC inverter. Here we see that the arrow is bidirectional. This means during the regenerative action, the power generated from the speed the motor running at some speed, the power will be fed back to the DC link using the reverse anti-parallel diodes connected to the MOSFET switches in this DC to AC inverter. Because in DC to AC inverters, you can say DC to AC converters, or simply you can say inverters. Here six switches are there, and two switches are in each leg, and each MOSFET has the anti-parallel diode. So anti-parallel diode direction is in terms in the direction of the positive of the DC link. So the power of the motor during the regenerative action can be saved in the DC link. Here in the DC link we have the battery. The battery is rated 1 minute, sorry. हेलो, अभी लेक्चर चल रहा है, बाद में हम बात करेंगे। हूँ बाद में बात करेंगे, लेक्चर चल रहा है। So this is the battery, and the DC to AC inverter. Uh, Suppose we have the BLDC motor that is rated at 48 volt, because in the BLDC motor and its controller, often it is written it is operating at 48 volt. Suppose so, 48 volt is the rating of DC link. So we have also to connect the battery of 4800 volt. Okay, here what we see, how this DC voltage is available here by fuel supply to the fuel cell. Here this is the fuel processor. We can use any carbonic fuel like methane or methanol, whatever. Here you can use the gasoline. So the fuel processor provides the hydrogen output from this, the output of this block, and this is going to the fuel cell stack. Stack means there are multiple number of fuel cells connected in series and parallel to meet the power requirement of this DC to DC converter. Overall power requirement of this motor and this transmission. Okay, so here how the fuel processor and stack is controlled. Uh, this is controlled using the vehicle system control. Vehicle system control, it takes the signal also from the fuel sensors and electronic control for the stack, and also sends the signal to the sensors for the fuel management. Means if the fuel is going or not at proper rate, whatever the reference rate was given, this information is also going to the vehicle system control. Okay, so here we can see that the DC to DC converter operates the fuel cell at maximum operating point, maximum power extraction level. So this will also provide the signal to the DC-DC converter. So everywhere we have the feedback as well as signal given to the block, because bidirectional means we have also the facility of feedback, what is the existing value and what we want to give, what we want to control. So we can also give the control value as well as we can also take the present actual value running in this system. Okay, so now I will come to the simulation part. So, is it okay? So,
Yes, sir.
now this is the new model here, and MATLAB is introduced to everyone. This is the Simulink library browser. Here we have the different toolboxes and systems. Here, these are the commonly used blocks. This is the integrator. Integrator is generally used to add the values, add the samples. This is the logic operators like AND, OR, NOR, NAND, these types of gates. Like suppose we have two inputs coming, and if both the inputs are say one, then in case we have to take the decision. So this has to be and if any one signal is one and one signal is zero, we have to take decision. In that case, we have to select here. Same block will provide the every block, every gate, and or nor XOR every gate. So here this is the bus creator. Multiple inputs are there. We can integrate multiple inputs to the one line, and in the same database, all the inputs will be traveling. Here the bus selector. Suppose any bus is there. There are multiple lines. So we can select any output from that bus, and we can use it for further mathematical analysis or further control simulation studies. Okay, here this is the constant. uh, we can vary any value. We can keep it 1,000, 10,000, whatever value we want to keep it. We can simply double click here and put the value. This is the convert. There are different types of data. Like here you have uh, floor. You can floor the values and uh, uh, different like binary values you want to get, double values you want to get. So one type of data is here and they are not matching with the output data, then we have to use this flag to match the input with output. This is the delay. Suppose any output is coming and we want to delay it one sample, then if we use this flag, then the uh, previous sample will be available in the output of this terminal. Okay, even we give the present value, but here we will get the past sample. Even we give here the present sample, the past sample will be available at this terminal. This is the demultiplexer. Multiple inputs are multiple value variables are traveling in one line, so we can separate out them in different lines using the demultiplexer. And this is the discrete time integrator. Discrete time integrator is the conversion of this in the discrete form. So in the discrete form, this is the same, and in the continuous form, this is the same. So both these blocks are same. This is again, if we want to multiply anything, we can multiply this. If we can keep either 0.5, 0.1, whatever values we want to keep here, we can multiply also by 1,000. Suppose here we have input value of 1, and if we keep here 1,000, then here we will get 1,000. Okay, so it will be multiplied by 1,000. Here this is the ground. Okay, here this is the uh, terminals. Suppose uh, we make some subsystem, and inside that subsystem lots of Simulink connections are there. So if very large system we are making, then we can make some part of that control system as the uh, subsystem. So this subsystem will have some terminals, input terminals and output terminals. Output terminals will be like this. If there are four terminals, then one terminal will be one, another terminal will be two, and like this. If there are four inputs, so one terminal will be one, another will two and three, like this. So we can make any control system as a subsystem. I will later illustrate you how this can be implemented. This is the product and this is simple relationship. If the upper value, here we have the relationship. So if upper value is less than this value, upper value is less than this lower value, because we have using the, we are using here the less than. So if upper value is less than lower value, it will give the output 1 logic. Okay, here this is the saturation. Saturation means upper saturation and lower saturation. What should be the minimum value? What we have to keep the minimum value? What we have to keep the upper value? So during sometimes we, when we control the systems, we have duty cycle which is going above suppose 1.1, and duty cycle can never go 1.1. So we have to limit at our desired value. Suppose we can limit it at 0.99, and sometimes the duty, suppose duty cycle in DC-DC converter never goes negative. So in this case we have to limit it up to 0. So this saturation can be used. Okay, sometimes in AC systems we have positive one and negative one duty cycle maximum, 0.99 positive and 0.99 negative. So suppose if positive and negative values are going more than 1 and -1, then we have to control that. We have not any requirement of duty cycle more than these values. So we have the saturation. Suppose we have we have maximum flow rate of 20 liter per minute, and uh, so by some control it is coming 21 liter per minute. So is it possible to use this flow rate in uh, uh, fuel cell? No, we have to limit it. So these saturation block can be used for limiting the values, input values. Whatever the value will come here, the limiting value will be here. Means within that they will vary. But if they are crossing more than the maximum or minimum value, they will not vary. They will saturate. Okay. Here this is the scope. Simply everyone introduce of how to use the scopes. Here you can see um, we can change the number of terminals here. We can change the style of the lines. We can change the style of display, everything. So we can make, like here we have subsystem. Here this one terminal is available inside here, and one terminal is available inside here. So this is the subsystem. Inside of the subsystem we have two terminals, and any system can be put between these two terminals. Okay, here this is the sum. We can increase the number of summing points or subtraction point. We can use the minus also here, or plus also. This is the switch. This is the switch. This is mainly used for logic. If we have some input here greater than 0, then it will give this. If it is less than 0, it will give this. So this is the trigger. Means at particular condition the different outputs will be there. Okay, now we have some continuous sections. We have transport delay, we have state space model of some system. So these are the basic. What is the main requirement? We have to study the uh, logics here. This comparator, it is very important everywhere. This comparator is very important. This gate block is very important. This relation operator is very important. We give here any value using the constant block, and if any value coming here is less than this lower terminal, the output will be 1. So this is often used for generating the triangular signal or PWM signal from this. Okay, here math operations are there. We can generate the absolute of any value. Suppose it is negative or positive. This is addition. You can also convert it in subtraction. Here you can divide any value. So there are different blocks here. You have sine theta, cos theta. You can use the cos theta, tan theta. Here there are multiple numbers of trigonometric functions, and when wherever there are required values, you can use these functions. Like you are giving the theta 0 or 90 degree or 360 degree, whatever, then this will convert in sine theta and cos theta. Here, this is the sinusoidal wave. If we have some input value of time, depending on the omega t, it will give the output. Okay, so there are lots of systems here. Gain is already known to you. This is some is if you give magnitude and angle, it will give the some uh, magnitude versus angle value, or you can say it is the complex system, and it will provide the output. Like any complex number, you have the magnitude and angle. Here you can use the math functions. Here one function is shown e raised power u, and remaining functions, when you click inside that, you will get large number of functions inside that. Okay. Here one important portion is the sync. Here you can use the display. This will provide the value at the last, whatever value at the last. This will provide the variation of the values with the time, but it will not have the terminals. It will simply whatever value you assign in this, that value will be shown here. Here you have the terminal, but here you don't have the terminal. This is the floating scope. We will not require the connection with any line. Simply you assign that, and it will take the value. Here this is having the terminal. Here C mount means the variable, suppose any scope is connected to some switch or any voltage value, and you want to take it as some variable in the workspace, you can use the C mount. Okay, and this is the XY graph. Suppose you have X and Y values, some uh, some robotic arm is moving, and you can uh, by how much angle it is, then you the end effector of that robotic arm have the variable X and Y. So movement of that end effector you can see by using this XY scope. Okay, this is the source. This is very important portion of the Simulink, and here this block is very important. This block is generally used for generating the triangular signal, which is often used for generating the duty cycle and PWM signals for switching, uh, for DC-DC converters and inverters. Okay, so this repeating sequence is very important. Here the ramp, suppose we want to ramp the fuel flow rate initially during startup, then we have to use this ramp block. This is the pulse generator. If you have definitely the known duty cycle and fixed duty cycle, you can use this block to generate a definite PWM signal with that duty cycle. Okay, so now I will show you the main library here. This is the electrical library. Basically, we have to study this electrical library. Here in this electrical library, what are the main things we know? Specialized power systems. This block is very important for us to study and simulation of these fuel cells, battery energy storage system, together with the uh, like electric vehicles, PMSM, BLDC motor, everything will be available in this specialized power system. So here, what you have control and measurement. One is electric drive. This is the facts and fundamental blocks. So in renewables, you have wind and solar renewable energy examples. You can see the solar PV here. You can see the wind generators here. Okay. So this is the renewable energy related blocks here. Here the facts. Facts means flexible AC transmission system. You have DC-DC converters, DC to AC converters, and a very large power capacity. So that are called the facts together with implementing the power quality also. Here you have the electric drives, AC drives, DC drives. AC drives have the brushless DC motors, DTC direct torque controlled induction motor drive, field oriented controlled induction motor drive. So these types of drives are also important for electric vehicles. This is ready-made blocks. Generally, we use whatever I use simple PMSM with trapezoidal back EMF set at its block, and then making the inverter and implementing the different censored and sensorless techniques to control the inverter. Okay, so I have mostly used the simple fundamental blocks. This is the DC-DC converter, like operating the DC motor in two coordinate system, two coordinate chopper system, four coordinate three phase rectifier DC drive system. Means you have we have the three phase rectifier that is operating at four coordinate. So these types of blocks are there. Extra sources you have battery, current control. Um, battery charger, constant current, constant voltage battery charger. Here fuel cell stack are available here, and super capacitor. Okay, what is the super capacitor importance? Super capacitor mostly provides the power during the fast transient of the high power, and supplies the load current, and during the sudden power requirement, it stores the power in the capacitor, or during the sudden regeneration action it can save the fast power, because the capacitor cannot hold the power for long time. Super capacitors are very large capacitors. The values may be 1 farad and 5 farad or 10 farad, whatever. Farad is very large unit, and microfarad is very small unit, generally used in the small systems of power electronics. So we have this system. Now we come to the fundamental blocks. This is very important, and presently we are going to use the lots of components from this. We have the electrical sources like AC source, AC current source. This is the AC voltage source. This is the current controlled source. Means whatever value we give, it will provide a current. Here this is the current controlled voltage source. Means whatever value we here give, it will provide the variable output according to this value. So here the constant voltage output, that is DC voltage source, is available here. We have three phase source, star connected or delta connector we can use. Here generally three phase source is star connected. Here we have neutral terminal available and three phase programmable source. Okay. Now we have the elements. This we have the very importance of this element. It is RLC branch. Wherever we want to use this resistance, simply we have RLC, R, L, and C separate. Everything we can make here. We can use either resistance only, or inductance only, or combination of Na2, or combination of all three. We can use this block to make this. If we use the power, we have the power capacity, active and reactive power, capacitive reactive power, inductive reactive power, and resistive power determined, predetermined, and that is the power requirement of the load. Then we can set this element there for the load. But generally, in this simulation, we will use this block for capacitors, for inductors, and resistance. So all other can be discussed later here. Circuit breakers are generally used for connecting or disconnecting any system. Here C is the control input. When suppose initially the circuit breaker is open and uh, uh, we give the zero input, and we have set here that for zero it is open. Then when it will get one, it will close, or it can be reverse of that. When for zero it is closed, it will get one, then it will be open. So this is the basic block interface elements here. uh, Now here machines, we have different machines: asynchronous machine, induction motor. We have squirrel cage induction motor. We have no any rotor terminals here. Here asynchronous machine, we have three terminals available for one rotor induction motor. This is the DC machine. We have field and armature terminals here. We have simplified synchronous machine. We are giving the mechanical power, and we are giving the excitation. We have three phase output here. We have the split phase induction motor. We give the AC supply to this, and we will get the speed, everything, torque, and so here synchronous machine. These synchronous machine blocks can be used for BLDC motor also. Here there is the option for you can say option for trapezoidal back EMF, that is for BLDC motor, and sinusoidal back EMF, that is PMSM or synchronous machine. Okay, here you have measurement. You can either measure the current, you can measure the voltage, you can measure the impedance at some terminal, between some terminals. And here three phase measurement. If you have a three phase, then VABC means VABC will be calculated. Here you can see here VABC and IABC is coming out of this block as measurement. So VA, VB, and VC, three phase voltages will be available here, and three phase currents. Okay, so this is the simple introduction of this Simulink library. Here there are various power electronic switches are there, and some converters, two coordinate DC-DC converters. So basically from here we will use the MOSFET and we will use the IGBT. So IGBTs are not very fast as compared to MOSFETs, but it can carry high power capacity. Here this is the ideal switch. This is general switch. It can either represent these IGBT or a MOSFET or anything. This is the generic switch, and this is the gate turn off switch. This is the diode. Okay, so and this is the thyristor. So in any power electronic circuits, we can use these power electronic switches. And power GUI. This is very important block during the simulation of any power elements. We generally have to use the power GUI. If we don't keep the power GUI block in that simulation model, that will not work. Definitely, we have to keep this block every time when we are simulating the power electronics and power circuits. So I start with the simple simulation of um, fuel cell. So here, this is the add to block, add the block to the model and title 2. We have this block. Okay. So this is not having any terminals to input the things. Simply, if we connect the voltage measurement here, voltage measurement block here. We will simply see this output. What output comes when we do this? So for looking the variables, we use the scope here. Okay, so this is the scope, and now we take out what are the values of the fuel cell. So for taking out the values of fuel cell, we have to use the bus selector in this, and this bus selector, we can use any value from this terminal. Suppose when we double click this, we have various values of the fuel cell. We can either take out the voltage, current, we can either take out the stack efficiency here, all of these. Suppose we want the voltage to be increased by
I think a trainer is having some kind of internet issue. Please don't leave the room.
सर लीव कर सकते हैं।
हाँ बस थोड़ी देर रुक जाइए, सर को आ जाने दीजिए, उसके बाद आप जा सकते हैं। वो सोनी सर अभी कनेक्ट करने की कोशिश कर रहे हैं।
ओके सर।
Hello, I'm back. Hello, can everyone see the screen?
Yes, sir.
Okay, so I was in the stack. Okay, so I was discussing this bus selector, how we use the bus selector in the fuel cell and take out the different values. Suppose we want to take out these three values, then we push the control button of the laptop and we click on these three and then we select. Okay, then apply, and this is okay. Then we have these three values. We can give it directly. Another value we have, we can directly connect here, and we pushing the left click, we can connect it here. So when we simulate it, happens. Just see. Here we can see that it is saying here in voltage measurement. Okay, so it needs the power GUI block. Okay, what I had said you that power GUI block is always needed. So here simply you have this block to add. Okay, so right click in that block and add. So here we can operate it in continuous form or we can operate in discrete form. Because we are dealing here with the MOSFET also for the boost converter. So we can use the discrete values. Discrete values had discrete samples, and some time some resources of the controller can be saved. In continuous time, every small time we have to take the samples. So the resources of the controller in MATLAB are used to very high. So simply here we can give 1 e raised power minus 6 sampling, means we have the 10 lakhs of sampling frequency in this simulating platform. Okay, so here we have set this value, and now we simulate what happens. So now it is simulating. Okay, now it is running. And okay, continue. So we see what happens in this output. Can we get here the voltage or not? So simply here voltage is not available. Okay, what we here get here, can we get the voltage and current? Here there is zero. This is the zero value. Okay, if we have to operate it very fast, we can use this. You can use lower sampling rate. Okay, higher sampling time. So it will have low numbers per unit time, and it will run very fast. So now we have selected this sampling value, and it is simulating. We see what happens here. These values are coming. So now, because there are multiple uh, things in this one display, so we have to see this layout. And there are three values coming in this scope. So we have this. What is the current? Zero current, because no load is connected. 65 load, because open circuit voltage is given by the fuel cell. And stack efficiency 0, because no output, no voltage output, and no work is there. So now simply what we see inside this fuel cell, this fuel cell is simple model. Why simple model? Because this is not having any variable input. This is simply fixed at its rated nominal. Okay, so here nominal operating point is 133.345 volt. The suppose we set here 6 kilowatt 45 volt DC. Okay, and we apply. And what happens? We have 65 volt V0 and V1 63. Nominal operating point I nominal and V nominal is 133.3 and 45. Yes, you can see simplified model means we don't use the input values of different air flow rate or anything. We have simply the values of nominal voltage and maximum operating values. And now this is the signal variation. Here there is no signal variation used. This is the fixed simple model. So uh, here we are not using that. Here proton exchange membrane fuel cell, solid oxide fuel cell, and alkaline fuel cell are modeled in this block. Okay, only for these cells we can model the Simulink control diagram. or we can simulate. Okay, this is the fuel cell dynamics. What is the response time of the fuel cell? 1 second or 0.5 second or 10 second, means at what time the reaction starts, because initially just regular reaction starts in the fuel cell. So this is the fuel cell dynamic response time. Here, suppose we use the detailed model, because detailed model generally we have to use because we have to control the flow rate of the hydrogen according to the required current by the load. So we have nominal composition 99.595. You can take a snapshot of this, and then I will ask, you have to say me what are the values. Nominal composition of H2O2 and H2O is 99.95, 21%, and 1%. Okay, so water is 1% in the air, 99.95 in the hydrogen in the fuel, and oxygen in the air is 21%. This is selected. Okay, this is rated value of PEMFC for giving output 6 kilowatt and 45 volt DC. Means if we provide these values to the fuel cell, means we have 65 number of cells, with each cell having 55% efficiency. We have 65 degree Celsius of temperature, and we have nominal airflow liter per minute is 300, and 1.5 bar fuel pressure, and air pressure is 1 bar, means at atmospheric pressure. Okay, so we have we have these values. If we operate at this value, these all flow rate and everything, we will get 6 kilowatt 45 nominal value, nominal output. But we have also the maximum value of that. Okay, we have also the maximum rated values of this. So we can see what are the maximum values. So here you can see. Here, fuel cell nominal parameters are given. The fuel power is 6 kilowatt approximately. You can see 5998.5 watt. Maximum is 8325. Okay. Maximum is operating at maximum pressure and everything. Fuel cell resistance. This is the fuel cell resistance R. Okay. Nonce voltage of one cell 1.1288. This is due to the chemical reaction. Nominal utilization US2, UF2, we were using 99.56 and 59.3. Nominal consumption of the fuel 60.38, and air is 143.7. Exchange current I0. So every value is given here. Okay. Whatever we have studied here, the value of that is given. So now see the VI characteristics are, we have also the polarization curve. In the polarization curve, this is the polarization curve. You see, this is also called the voltage and current. So we have 133.45, 133.3 and 45 volt. So what is the multiplication of that? This is the power. Power is 5.998, yani 6 kilowatt. Here, this is the nominal, but for maximum values of everything, we have 8.325 kilowatt. So this is the nominal value. Always we have to target the nominal maximum value, nominal value. Okay, because we have to operate the fuel cells at nominal values. Okay, this is the power versus current. Okay, everything can understand.
Yes, sir.
Yes, sir.
Okay, okay. Now we connect the load across this. Okay, simple load. What happens when we connect the simple load? What is effect in the power and the current? So we can use here simple element here, electrical, and we have some specialized power system. We have fundamental blocks, we have elements, and we have RLC branch. We add the block branch in this. Okay. So we simply use the resistance and we keep 1000 volt. What happens at 1000 voltage? Whatever the current will come, the power will be very low. Okay, because it will take low current, so power requirement will be low. Because it is definitely fixed at its nominal parameters. At nominal values, it will give the nominal voltage and the nominal power output. But the power current is varying according to the resistance, so it will give the voltage equal to 45 volt, but it will reduce the power current because it has very high resistance. So what we see here, the voltage and the current, we see the current at this terminal. Okay, so this is the current. Okay, in current block you have one plus terminal and minus terminal. Simply from where the current is coming, we have to connect the plus and where the current is going, the current minus. Okay, now you can check the current here. What happens now? What is the effect on the current and everything? Yes, you see that the current is 0, voltage voltage is 0, current is 0. Current is 0 and voltage is 65. Because you can see in polarization curve that uh, it is not controlling the uh, current. The current is not coming out because we are not controlling the air flow rate according to the it has not ramped. Okay, so what we have to do, we have simply to use its detailed model and then to use the signal variation and fuel flow rate. We have to use this fuel flow rate. In this, you can see when we have used this detailed model, we have available terminals of this variation fuel cell. Okay, so now this terminal has come, and if we control the fuel flow rate according to the current, bit higher flow rate than the required for that current. So we have a block here which mainly uh, provides us the fuel flow rate depending on the current. Okay, so whatever current we are taking out from the system, because here it is not giving. Okay, so initially we are giving it this value. Okay, and now this is feedback to this, and this has the parameters. How many number of cells were there when I had said to take the snapshot? 65 cells. What was the nominal utilization of hydrogen? 99.56. What is the operating temperature? 65 in that. What was the fuel pressure? 1.5. What was the hydrogen composition? 99.95. Okay. Have you seen in that block? If you don't have seen, then I can show you here. These all the values are given here. Okay. See. Clear? So we have simply to keep these values here, and now we simulate it. What happens now? Why it happens? Because initially it is not ramping. Initially it is not ramping the voltage. Okay, clear? If we increase the suppose if we decrease the resistance, what happens? Everyone understands the operation? What we are doing here?
Yes, sir.
Yes, sir.
Here we can see that when we have reduced the resistance, the current requirement increases. Okay, so the voltage goes down to 60, and the current increases to where you can see current increases to this 6 ampere, 60 and 6. Okay, so higher the current requirement, higher the flow rate, and it will maintain. Okay, here what was the polarization curve? If we see the polarization curve here for 6 ampere, what will be the, this is the 50, this will be 10, 20, 30, 40, 10. If you select the 5 or 6, you have 60 voltage. Means it is operating. It is operating by using the flow rate controller, which depends on the current. Okay, it is easily understandable to everyone.
Yes, sir.
Yes, sir.
Now suppose we have some battery here. Okay, what is the battery? Battery operates at constant voltage or constant current? Anyone can answer?
Yes, sir. Uh, Constant voltage, sir.
Until it is fully charged, it works at constant current because we need the constant current charging. Okay, and it has not the constant voltage. When it has reached to the sufficient SOC and it has no an increase in the voltage, then it will work in the constant voltage mode. Okay, so suppose we connect here the battery. Okay, and we also check the SOC of this battery. Okay, for looking the SOC of battery, we have to take the signal from bus selector. Suppose we copy this bus selector and paste here. Okay, so okay, now we have large number of values from coming out from this measurement terminal. So what values we can take out? We suppose take these values, all values. Okay, then we have one terminal here, one terminal here, and one terminal here. So voltage of the battery, current of the battery, and SOC. If the battery takes current, then SOC will increase or decrease. State of charge of battery. Who can
Increases,
answer?
sir.
Yes. If battery gives the current, SOC increases or decreases. What happens? Anyone can answer? So reverse of that. Okay. So now simulate this system. Means what it should happen? It is storage system, and it can store the maximum value as per its ampere hour capacity, whatever the time it is taking. Okay, depending on time, how much SOC is stored in that state of charge, whatever charge is stored, SOC will increase. So after the simulation, what we get here, you can see here, we see that the current value, current value is this. Okay, 20 ampere, and no, voltage value is 20 ampere, and the current is increasing very high. Means now, because we have the battery also, and we can then not use, suppose we use the very low load, then definitely all the system, uh, uh, we also take what power the stack is giving out. So we use the multiplication block here in this. Okay, so suppose this 1 and 2 are the current and voltage, and this one is power. Okay, so upper is power, current and voltage. Okay, so now we simulate what happens. It is giving very high and low current. There is fluctuation. So for this fluctuation, some device which works instantly by storing the variation in the control. Which device is like that? Capacitor. Okay, so we can use the capacitor here. And we can, because it is very high value of fuel cell stack, we can use 5000 microfarad, suppose. Okay, and we have connected here. what happens now? Can this fluctuating voltage be controlled? So for this variation of the current, what we have to use? We have to use the boost converter. This boost converter, here we can also see the power output. What is the power output during this operation? Here the power output is like this, very high variation, but it is limited to approximately, we see by examining these values, we can see the what will be the average value. Okay, it is fluctuating, so we can see that it is operating at, this is like this, up and down 50%, so average value may be something like this here. Okay, so we have to use the boost converter here so that our system operates at maximum power point. So here we have one simulation which is already work ready for study. Okay, the same system is here. You have one inductor in series, we have current measurement block, we have MOSFET, and the MOSFET is provided with the pulse input using this duty cycle input and compare with triangular. Whatever duty cycle we will provide, depending on the this duty cycle, there will be a pulse, and this pulse will control the boost converter, and boost converter switch will solve inductor during on period and open this circuit during off period, and whole current will flow to this section. This will also be stored in this you can say capacitor, and also it will be stored in the battery if it is connected, or it will go to the resistance. Here the voltage of this and this terminal is measured here. So here in this measurement, what we have, the voltage, current and power, okay, of the fuel cell. Here the battery voltage and battery current is here. You can see the boost current. After boosting, what current is going to the load, and the output power to the load, your output voltage and output current. Okay, so P out is here, and this value is the current to the battery. Because we have disconnected the battery, so it will not provide the any value greater than 0. If we, this is the same system connected with the boost converter, a battery and a resistance. Okay, so what happens and what is the effect of duty cycle? Here one thing is, this is SOC. We have taken here the SOC only, state of charge of battery, and initially the battery was set at 20% state of charge. You can see in this block. Okay, because we are not connected here, the battery is not connected, simply SOC will remain constant. Okay, why it is not continuing? So it is running. Okay, what we see here, because we are not taking too much power from the fuel cell, only we have a certain duty cycle and certain voltage will be there in the output of the boost converter. So only the fuel cell is only providing the 400 watt. Here the fuel cell boost converter voltage is approximately 660 volt. Okay, here the voltage of the fuel current of the fuel cell is you can see approximately 6, and this is the 60. Okay, the current output at the resistance is 6 ampere, 6 ampere, and the this voltage output, this is SOC of the battery. This is the SOC of battery, and this is the power output. And the third terminal from lower is one. This is the duty cycle. Okay, so here the duty cycle is set at 0.1. Okay, what pulse is coming here? We can see the pulse here. So this is the pulse. Okay, we have calculated here. So you can see this. Okay, so not proper pulse is coming. Now if you means if we change the resistance simply, if same resistance is there and we change the duty cycle, suppose we change the duty cycle to 0.9. Okay, point, then what happens? You can see that the fuel cell power has risen to the 6 kilowatt. Okay, and the power output is this. And what happens actually? This is SOC of the battery. Here the SOC of battery is 0. Why SOC battery 0? Battery current, oh, sorry, view layout. Here you can see this is SOC of the battery is 20 and the battery current is 0. Okay, so you can see here various values, and because we have operated the boost converter at maximum duty cycle, it will be okay, maximum power. Now depending on this, we can operate the fuel cell at maximum power. Now if we connect the battery, what happens? Suppose we have connected the battery and we have operated the duty cycle at, we can also do the closed loop duty cycle control. So am I audible? The screen is sharing.
Yes, sir.
So we are checking the simulation here. You see here that when we have connected the battery, the fuel cell is taking more power, and you can see that is SOC is increasing continuously. Means we are taking the power from fuel cell properly. Okay, means if even if we don't connect the resistance here, suppose we disconnect the resistance and connected the battery here. Okay, suppose we have removed here, then what happens? ramping up of the current of the fuel cell has been there, and estimate we are taking the value step somewhere is not giving the value. So we can see that we have connected the battery, then also it is giving the power. Okay. So we can store the power from fuel cell to the battery, and we can use the boost converter to vary the power output. Or we suppose the battery is taking the power, and some power battery is taking, and some power we want to give to the load. So we can do both. And suppose we have the variable voltage control device. Suppose ki BLDC motor is operating at voltage controlled mode. Then we have DC. This is the DC link for BLDC motor, and then the whole voltage closed loop voltage control will be here, and a voltage controller DC converter will be here. Okay, for BLDC motor voltage control. For current control based BLDC motor control, we have simply 6 switch bridge inverter, and PWM based current control of each switch will be here, and this portion will work for the DC link of the BLDC motor. So in this way, we can use the fuel cell to uh, operate the electric vehicles. I want to close the session now. If sufficient learnings can be provided to the students, students can respond, please. Students, please respond. So I want to close now the session, and closer comments from the organizing team should be given here.
Thank you so much, sir, for such an insightful and engaging session. We truly appreciate your time, effort, and the knowledge you have shared with us today. As a token of our appreciation, we'd like to present a certificate to our estimate coordinator, Dr. Shochetan Shoshi, and trainer, Dr. Umesh Kumar Soni. Sir, this is a small gesture to express our gratitude for your valuable contribution to this work. Please give me a moment for sharing the screen. Um, Sir, I'd like to request you to accept this, Dr. Suchitam Shoshish.
Suchetan
Sir, are you
Sashish,
here?
just minute. Just minute, I am calling you.
Okay, and next is for our esteemed speaker, Dr. Umesh Kumar Soni. Sir, I'd like you to accept this.
Yes, sir. I accept.
Um, Thank you, sir. And now I request Dr. Khadija Akhtar ma'am, the counselor of IEEE IUBT student branch, to give a few words of appreciation. Ma'am, are you present here?
Yes, am I audible to everyone?
Yes, ma'am. Please, the stage is yours.
Okay, thank you.
सुचेतन मीटिंग
Thank
में आओ,
you very much.
तुमको ऑनर मिलने वाला है. सुचेतन मीटिंग में आओ.
You I really appreciate the effort you have made, my student branch have made. Thanks to all for showing your patience, and it was really important and it was really informative for all of you. So my special thanks goes to our speaker. He has made lots of effort on it, Dr. Umesh Kumar Soni. Sir, we are very much grateful and thankful to you. Session was really very engaging and informative. I hope our student got to know so many things from you, and in future maybe inshallah they will be learning a lot from other sources and as from you as well. They will connect you or contact you whenever they need. So my request you to sir, please provide assistance if they need your help.
Yes,
And
definitely I will provide help.
yes, and really we are very much thankful to you. It was really engaging, and this technological time learning about renewable sources is really important. So the effort you have made, it is really outstanding. So we appreciate and we acknowledge it. So inshallah in future we will be connected with you for more updated knowledge, updated technology and everything. So sir, thank you. And if
Thank you, madam.
audience, do you
Uh,
have any question from your side?
Definitely we can ask.
Yes, if you have any question, you can ask sir. He is very helpful. So I think you can reach him if you have any kinds of questions, any
Chetan connect
queries.
karo.
So sir, I think they don't have any questions. If you provide the recording, that one will be better for them to do some self
Yes, definitely I
study.
will provide the recording. And
Yeah,
Suchetan is
yes.
just joining. Suchetan is just joining here. About to join. I have said him to join.
Yeah, yeah, yeah. Yeah, yeah, we are thankful to him as well because he has helped a lot for the smooth conduction of this session.
Thank you, ma'am.
And our student branch chair and all of my student branch members, they are really working hard. I appreciate all of their effort they are making to upgrade the reputation of our IEEE student branch as well as our IEEE department and our university. So, sir, if you can keep everyone in your prayer so that they will learn a lot and they will be a good engineer, they will serve the humanity through their technological knowledge.
Yeah, definitely I will always be helping.
So, thank you all. Thank you for joining. So, I think with this, we
So,
will conclude the session.
madam, what I was saying, Suchetan is here. He was not
Oh, okay.
there at when the madam called him. Uh,
Oh, yeah, we have a small token
yeah,
of appreciation for him. So, moderator, can you please pass it to him?
yeah.
Yes, ma'am.
Okay, so share your screen so that later on just inbox it to him. Share the screen so that he will take the small token of appreciation from our side.
Ma'am, is the
I
screen
have to
visible?
unshare the screen.
No, 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 I can't see your screen.
I am
Uh,
unsharing screen.
oh,
Now you can share the screen. I am unshare.
Yeah, I
okay,
think
sir.
now you can share. So share both of the certificates.
Oh, sorry, ma'am. I think the previous one was not visible.
No, now it's visible. Yeah, yeah.
Okay,
So
ma'am.
yeah, yeah.
And this
Again,
is for
please share.
coordinator Dr. Suchetan Shoshish. Sir, please
Thank you. Thank you.
accept this.
Yeah, sure. Thank you for the appreciation. I can see the screen. No issues. It was a very good session, and I'm very grateful to be a part of it. Thank you.
Thank you, sir. And sir, this is your certificate. I was really sorry because I didn't know the screen was not sharing at that time.
Yeah,
So
yeah.
please accept this.
Thank you so much, madam, for this precision. We will definitely be helping in the future whenever requirements of the student and all the team of the students together with the faculty. We are doing excellent job during this session, and we will definitely help be connected in the future.
Okay, sir.
Thank you
Thanks a
very much,
lot.
sir. Ma'am, would you like to speak something?
No. I think I have said enough. So thank you, everyone. So inshallah, next time we will come with a new session, new topic. Any new emerging technologies, inshallah, we will make another session. Thank you,
Thank you.
everyone.
Thank you, madam. So students, feedback form will be so all the participants can now leave the meeting. Or I close the meeting.
Okay,
Thank you
sir.
very much,
Thank
sir.
you.